Swayam Prabha. Digital India. Educated India.
So, in the last class we looked at a nice property of irreducible Markov chain, that is positive recurrent. We said that it is going to be positive recurrent if and only if there exists a probability function pi such that it is the solution of the equation pi equals to pi p, right. So, in the last class we just showed existence of such a pi, and we argued that that is going to unique, right. But yeah, one of you pointed, who is that, you, right. So, about the uniqueness. So, he has a concern that whatever the method we started with, we had some way of construction of Bn's. So, we had this Bn's and this was a vector, and we showed that this as n goes to infinity, this was converging to some gamma, right. So, if I am going to take some, this is Bj, we said this was positive, but this is, we know this limit is unique, but you are starting with some method where you are going to start with some particular sequence and saying that that is going to convert some little. So, this whatever, and we somehow translated this, we take this pi equals to gamma, but after normalizing this gamma by dividing it by summation of gamma i's. So, by this method, I mean what are the gamma we got? Yes, this is an unique solution for the method we started with, but if you have started with another method, maybe you would have constructed another sequence and looked into its limit, maybe what is the guarantee that that would have also given you the same gamma. For uniqueness, I want that, right, irrespective of what method you are going to construct, when you look at the limit, that limit should be the same. That is what I wanted to show. So, in a way, the last construction we said, okay, for that method the gamma you obtained is unique, but we are going to say that that was a kind of hint for this. Now, we are going to say that that is going to be the unique whatever method you are going to use. So, now we are going to argue that if then any other pi exists, let us say which satisfies the relation pi equals to pi p, that must be necessarily the case that that pi is exactly equals to this gamma. So, okay, let us try to argue that. So, in the last class it was clear that this pi is a positive probability vector, right, because all these gamma i's are positive. Now, how to show uniqueness? Now, let us say that pi is any probability vector with strictly positive elements in this, and then let us say that is a solution of pi equals to pi p, okay. So, some pi which is going to satisfy this. Now, we are going to argue that this pi is nothing but this gamma, okay, this pi must be necessarily this gamma, okay. Now, how we are going to show that? Here this pi is such that summation of pi I equals to 1 and pi I is equals to 0. So, let us assume that this pi is such that it is a probability vector with strict positive elements in it and it satisfies this relation. If it satisfies this relation, I already know that by repeating this recursion, I should be able to get this for all greater than k equals to greater than or equals to 1, okay. Now, what I do is I will add this for k times. So, this is true for any k equals k, right. Now, I will take this for k equals to 1 to up to n and then add all of them. So, if I add all of them on the right hand side, I am going to get n pi, and on the right hand side I am going to get and let us divide them by n. Okay. Now this guy on the right hand side, if I just slightly reorganize this, I know already how to handle this, right? We have already dealt with how to handle this. We have already said that if this is going to be, so if only if you are going to look into this quantity is going to be finite if my state is transient, right? And in that case, if I am going to divide it by n, anyway it will go to 0. We have shown that this quantity in the limit as n goes to infinity already goes to 0 if my state is, and I am now looking at 1 by n and null recurrent. But if it is not either of these two, then it goes to some constant which we said as gamma j, right? So now just do this, you let n goes to infinity. So the left hand side is anyway constant, what is changing is the right hand side as n changes, and where this limit is going we have already shown that this is gamma, right? So then this pi is actually equals to gamma only. And that gamma is what? That gamma is a specific vector which is the limit of my sequences. Now what we have just argued is this pi, whatever this pi that satisfies this relation, that pi is equals to this gamma. Right, there is a pi multiplication here, but when you look at component wise, that what we showed, right? So now this is in a vector format, you take a specific component j in this and now look at for that. When we look into that, this quantity is going to be turned out to be simple gamma j, and now this is like a probability vector, right? So it will just add to 1 and you will just get the constant gamma j for that, and now just look at the vector. Just the same argument we did last time, except that I am just writing compactly it for the vector here. Okay. So now we have done the, what we started proving was only the only if part, right? We are trying to we were trying to show that the necessary condition that if my Markov chain is irreducible and positive recurrent, then the pi that exists here, that is there exists a pi which is a solution of this and which is also unique. Now we want to say that, suppose let us say we want to show the if part, that is the sufficiency. What we want to show now, if indeed such a relation holds pi equals to pi p for some positive probability vector, then my irreducible Markov chain is positive recurrent. How we are going to show that? So we are again going to show this by contradiction. Suppose assume that you have a irreducible Markov chain and let us say it should be of one type, right? Either it should be transient, positive recurrent or null recurrent. Suppose let us assume it is transient or null recurrent. So I am assuming, so assume pi equals to pi p, and then Markov chain is transient or null recurrent. Then for this we know that this quantity here goes to 0 as n goes to 0, right. And again going back to this previous step here, what I have, that is pi equals to pi 1 by n and k is equals to 1 to n p to the power k. And if I apply my limit as n goes to infinity, what does this say? This says this guy goes to 0, right. But what is this? We have assumed this pi vector to be positive, strictly positive. So this is right away going to give us a contradiction. So it must be the last case. If this relation holds, then none of this should be possible, a contradiction. Infinity, yeah. So this relation should be true for any n, right. So this is this relation, whatever we wrote, this should be true for any k. So I can just add all of them and get it for any n, and then I let n go to infinity. Okay. So now our part is complete. So if you end up with a irreducible Markov chain, then how you are going to ensure that that is going to be positive recurrent? What you first do is take this transition probability matrix, check whether it has a solution pi equals to pi p, right. If it has a pi that solution and all the components in that are going to be strictly positive, then you conclude that this is a positive recurrent matrix. Okay. Now what we did is we took a irreducible class, right, and we just focused on that. What if my Markov chain has many communicating classes which are all closed? For example, how does this result extend? So let us say I have so this is my state space S. I have one communicating class 1, one communicating class 2 and one communicating. So let us say my Markov chain reduced into these 3 communicating classes, and let us say each one of them is a closed communicating class. So then what would we say? Okay, if that is the case, okay, just focus on this and on the states here, then you can think of your Markov chain on this state space is irreducible, because your entire now state space is one communicating class, and then we did just study this. But suppose your Markov chain has multiple things like this, so how you are going to extend results like this? Now is it the case that if I look at my solution on the entire space for pi equals to pi p, will that pi is going to be unique? Okay, let us do this. Yeah, it could be unique for C1, C2 and C3, that we have already shown. Okay, let us say, let me take A1 here, which is the solution of this to this. So be watchful here when I write P1 here, this is the translation probability matrix reduced to the states in this class. So for this entire thing there is one translation probability matrix which is of size mod s into mod s. But now this P1 is that portion of this matrix which corresponds to this state space. That is again a translation probability matrix, right, because you have just restricted yourself to some particular rows here. And similarly E2 equals to now all of this A1, A2, A3 are according to us unique because we have just focused on that particular communicating class. Now what can we say? So now extend this to this kind is equals to pi 1 equals to pi 1 over entire p. Now what is this pi 1? Pi 1 is same as this A1, but on the places where the states are not included in this state, I am just going to append zeros there. You are getting a sense of what I mean by this. So pi 1 is still on the entire S states, but it is going to be some A1 here and zeros otherwhere. So that means this some portion it is A1 that is corresponding to the states in this class, and I am just appending zeros in the other places. Similarly pi 2. I mean the position where this A1 and A2 lies need not be at the same, this is just for my representation. So if you are going to extend like this, you can still check that pi 1 here is going to be a solution of this equation still. This is going to be the case because transition from this class to this class or this class to this class, those probabilities are going to be 0, okay, or this are not there. So because of that, even if you extend it like this P will be such that for the portions corresponding to zeros here, the corresponding elements in P is also going to be 0 because the cross probabilities are going to be 0. Just check that this is indeed going to be true for all of them. Okay, so let us say this is, I have all these are solutions, right, according to our. Now all of you know what I mean, what is a convex combination of two vectors, okay. So let us take, this is a probability vector, this is a probability vector, this is a probability vector. Let us take their convex combination. Will it be a probability vector, right? This is going to be a probability vector. So now if I take lambda 1 pi 1, lambda 2 pi 2 plus lambda 3 pi 3, this is going to be where this lambda 1 plus lambda 2 plus lambda 3 is 1. Okay, I take lambda 1, lambda 2, lambda 3 which they are positive and they sum up to 1, and they have taken their convex combination like this. So let us call this another pi. So this is the same pi here. What I have in the entire Markov chain, I have now based on this pi 1, pi 2, pi 3, by taking their convex combination, I have obtained another probability vector which satisfies this equation pi equals to pi p. So this pi is now, I have such a pi where pi is lambda 1 pi 1 but lambda 2 pi 2 plus lambda 3 pi 3. But now is this pi unique here that satisfies this relation pi equals to pi p? What? Exactly, right. So this lambda 3, this convex combination, if you change this, so what are this? They are this lambda 1, lambda 2, lambda 3. You take any such thing such that you take any lambda 1, lambda 2, lambda 3 such that it satisfies this, then you will get another pi here, different pi which satisfies this. So on the whole thing, this solution pi equals to pi in p need not be unique. There could be many pi's that could solve this, and specifically these pi's can be obtained as a convex combination of the pi's we obtain on each of these communicating classes. Okay. Then, so let us look at another example, so far. So let us say I have some 5 states like this, starting from 0, 1, 2, 3 and 4. Okay. So let us draw these transitions. So let us say I have a Markov chain like this. So think of this initial state as you start throwing some coin here. Okay, you toss a fair coin, when with probability half you enter state 1, with probability half you enter state 3. Okay. So when you enter state 2 1, after that you either go to remain in state 1 or go to state 2, you go to state 2 with probability half, sorry 0.8, and similarly when you are in state 2 you go to state 1 with 0.2 or remain there itself. Now this 5 state Markov chain, in how many classes I can divide this into, and what are those classes? So will 1 and 0 communicate? No, right? So 0 and 1 can't be in the same group, in the same class, and similarly 0 and 3 can be in the same class? No, they can't be, right? But can 0, 1 and 2 can be in the same class, and 2 and 3 and 4 can be in the same class? So then what are the possible classes? 3 classes, right? So class 1, class 2, and this has to be in the separate one. Now what about class 1? So let us call this class 1 and let us call this class 2 here. 1 and 2 are closed, right? Okay. Now, so fine, you can have such a transition like, and based on that you can see what are the different classes here. Now suppose that you want to solve for this equation. It is still not one irreducible class, but suppose let us say you solve this and obtain some solution. For this case it looks like the solution is going to be 0, 1 by 10 and 4 by 10, 1 by 4 and 1 by 4. Just check this, I am just dumping this on the board. If you are going to start your Markov chain with this distribution as your initial distribution, okay, you right now this I have just told you this is the transition, I have not told you anything about the initial distribution, right. Suppose you solve this and you start this with this your initial distribution. We already said one property, what was that property? So x1, x2, x3 at every point it is going to remain in the same thing, right. Now then you can also then in a way that can also imply that if we start with initial distribution pi, then my DTMC is stationary. So we have already discussed what is the stationarity of a process, right? Okay. So if your Markov chain is such that if you are going to start with your initial distribution simply to be this invariant distribution, then it is going to be stationary. Right. So this is not a irreducible Markov chain here, right? So that was the case when it is irreducible. So now I am not saying that this is going to be reducible. This is an arbitrary Markov chain with different possible set of classes. Now you just still take this as the solution of this. Okay. Provided this pi solution happens to be a probability vector, you take it and make it as your initial distribution and then run it, then your Markov chain is going to be stationary. Yeah, so we have only ensured that my pi is going to be unique when I have a irreducible positive recurrent one, but here it is neither positive, sorry, it is irreducible and I have not yet verified whether these states are recurrent or what. So I have just said take a solution like this. So in that case I am not guaranteed to have an unique distribution. So that is the thing, right? Like if there are multiple solutions which satisfies this, and if you are going to start with those different possibilities, then your stationarity, your probability that your Markov chain is going to take a particular state in a particular time, that is going to be different. It depends on what is the initial distribution you have started with, and that you can have multiple possibilities in that case, in case if you have many possible pi's in that case. Yeah, let's say let's try to see a case where such a thing will not happen. Okay, when is a possibility? Can you think of any case where this pi equals to pi p can't be a solution? So at least there will be always a pi equals to pi p solution will be there, right? Because why? We know that we already argued that pi is a stochastic matrix, right? So pi has a eigenvalue of 1, and this pi is what we are basically saying, that this pi is nothing but the eigenvector corresponding to that one. We will always have, but the question is, will this add up to 1? If whether it is going to be, if not, if it is not going to add up to 1, is there a way you can make it and add up to 1? How? Normalize this, then you will have always one such pi which is going to satisfy this relation, right? Then you can start with that. Yeah, I can think of a case when it is possible. Fine, I have 1 as eigenvalue. If that eigenvalue will be such that 0 is the only possible eigenvector, yes. Yeah, so we have to think about an example for that. Then in general, I don't know like under what condition it holds, we have to basically construct an example. So in a way what this says, if suppose pi is equals to 0 is the vector, right? If rank is not full, it can have multiple solution. The question is, can 0 be a solution? No, we are not saying p equals to 1. So this is pi equals to pi p, right? So let's write it as pi into 1 into pi p. This is my value. So suppose this is all 0, this is anyway trivially satisfied. That is not an issue here, right? So okay, so think about this. Is there any transition probability matrix where my pi equals to 0 is the only solution for so come with a proper, so even forget transition probability matrix, just construct a matrix which is stochastic. We will have eigenvalue 1. Is there a matrix whose with eigenvalue 1 can have only 0 as the eigenvector. If that is the case, yes, then we will have. We have an eigenvector. When we say by default, let us say it makes sense only when the component, at least some components are going to be positive, right. If that is not the case, then this is going to be, this relation is going to be satisfied for any constant, for any eigenvalue. Thus, what all we are asking now is, suppose if I have such a relation, is it always the case that pi I is equals to 0 for some I, for some I? As long as one component is going to be positive, that is fine, right. I will come up with a vector which will not have all 0. So, what is that matrix, or is it the case that whatever p you are going to start with, we will end up with this. Okay, just think about this. I think we should be able to argue that whatever p you are going to take, I will end up with a pi in which at least one of the component is non-zero. So, because of that I can always discard the all 0 solutions. Okay. So, it looks like pi here is an eigenvector, but we have to just make sure that our definition of eigenvector is consistent, in the sense that that exclude the case that all the components being 0, right. We just need to ensure that. Okay, just check about this. Okay, fine. So, now what we have just dealt with the case when I have a reducible class, how to say whether it is going to be positive recurrent, right. So, now if it is not positive recurrent, there are, that means if it is not possible recurrent, that means I will not be able to find a solution pi equals to pi p, where pi is going to be my positive, is a probability vector with positive components, right. And by the way, notice that we have already also argued that if one of the component is positive in my vector pi, it must be the case that all the components are also positive. It is not that only in the solution only one component is positive and other components are going to be 0. Okay. So, we showed it, right, when we discussed the properties of this statement, when we said that if one component is going to be strictly, it means that all other components are also going to be strictly positive. How to ensure that? Now, what are the other properties? Do you have any other properties to say that if this is not going to be, I will not end up with such a pi which is a solution of pi equals to pi p and will have all strictly positive element. I may end up with some pi equals to pi p solutions here with some of the components to be 0, but that does not say that my reducible my DTMC is a positive recurrent class. For my DTMC to be positive recurrent, I want that the solution of this pi equals to pi p will be such that all the components in that are going to be positive. Okay, so I first, when I have such a big matrix, if I want to see that, first thing I will do is, okay, is this a irreducible communicating class? If that, try to find pi equals to pi p solution, see if all its components are going to be strictly positive, then you are done, you know it is a positive recurrent. If you happen to find this pi equals to pi p solutions with some of the component is 0, then you know this is not a positive recurrent. It has to be either transient or null recurrent. How to verify this? So, next we are going to look for a condition when we can say that this is going to be a transient. Okay.